This lesson we begin the very important topic of current and charge flow. Remember, so far we've been saying that we're in electrostatics, which is where charge exists and exerts forces and so on, but doesn't itself move. And then we kind of cheated and we allowed some charges to move anyway, but sort of in a quasi-electrostatic limit. Now we're going to talk about what does it actually mean when these charges flow, what do they do, and this will inform the rest of our study because it will lead eventually even into magnetism. So, what if we're not in electrostatic equilibrium? Then charge will flow. Sort of duh. We call the flow of charge current, and we symbolize it with the letter I, or maybe capital I. And yes, physicists are aware the letter I is also used for the imaginary unit. This is a historical collision, and we're stuck with it. It frustrates electrical engineers so much they often use the letter J, but they use it for the imaginary unit, really. Following the book we'll use I, lowercase I. Lowercase I is the rate at which charge flows along a wire. I is dq dt. And the idea being that we have if we have a wire, which is sort of a conductor that's been stretched out, and we pick some portion of it, so some imaginary surface of it, we count how much charge goes through that surface per unit time. The unit of current is the ampere. We usually call it just the amp, symbolized by capital A, where 1 amp is 1 coulomb per second. Ampere will turn out to be very important in the study of electric circuits, and so this was a noble historical attribute, though almost everybody forgets his name and just calls it an amp. So there we go. Every minute, 120 coulombs of charge flow through this cross-section of the wire. Like that, say. The wire's current is which of these? Well, we just defined I is dq dt. So here it's 120 coulombs over 60 seconds, or 2 amps. We define the positive direction of current to the direction in which positive charges flow, which makes sense. This is so-called conventional current. And we do this even though we know for metals the charge carriers are electrons, that is negative, and so flow opposite that. They flow in the other way. So we sort of need to distinguish physical current, which is the flow of electrons, from conventional current, which is the direction positive charges would flow in the circuit. The reason for this, of course, is, again, Ben Franklin picking the wrong choice way back when he decided which things gave us plus and minus, and the fact that it takes really long in the history of physics for us to discover that it is, in fact, the negative charges that are moving. So for most of electronics, you don't really care and it doesn't make any difference, but people had already settled on the positive direction being the current, so that's what we're going to go with. When an electric field is applied to a conductor, the electrons move. Opposites of the field, of course, curse you, Ben Franklin, but they bump into the positive nuclei and experience a drag-like resistance. As such, they tend to move at what's called a drift velocity with a speed of 10 to the minus 4 meters per second. So they kind of wander their way over, but for the most part, they're bouncing around in random directions. At this rate, it would take about 10 to the 4 seconds to travel 1 meter. That's about 3 hours. Yet if we discharge a capacitor or turn on a light, the effect is nearly instantaneous. How could that be? It's what I call the movie theater line effect. The wire is already full of electrons. We don't need to move a single electron from the power plant through the wires to the light bulb. We just need to bump over the electrons that are already there, so it can happen much more quickly. Here we see this illustration which says the 10 to the 11 excess electrons in the negative plate move into the wire. The length of the wire to accommodate these electrons is only 4 times 10 to the minus 13 meters, which is crazy. And then 10 to 11 electrons are pushed out of the wire and onto the positive plate, so it becomes neutral. And then, oops, I guess we really went this way. The sea of electrons is pushed to the side. It only moves a very tiny amount, though, which takes almost no time. And then they end up scattering onto this plate and end up charging that capacitor, or I guess in this case, discharging the capacitor. To overcome the internal resistance to electron flow, we need a source of EMF that keeps pushing the electrons through the wire. Otherwise, they'll just quickly come back to electrostatic equilibrium. Remember that EMF here is just this weird term for voltage. It's electromotive force. It's an old term. It's symbolized by this weird curly E, which is annoying to type and annoying to write, but we are settled with it because there are so many E's in physics. There's already electric field E and energy E, and now EMF E. And we can't use lowercase e because that's, of course, the exponential E and the charge on electron E. So we're kind of stuck with the curly E. why use EMF? Well, later on, when we have time-varying fields and so on, we'll see that it's a little bit different from just a voltage source. But batteries are a steady source of EMF, but there will be other ones that we'll run into. All right, the analogy they want to make here is because of friction, a steady push is needed to move the book at a steady speed. All right, and the idea likewise here, because of collision with atoms, a steady push is needed to move the sea of electrons at steady speed. We want to move the electrons this way, but there's some drag, so we need to have a force on them this way, which again, because of Ben Franklin, means the field has to be pointing this way. But to maintain the electric field, we have to have some separation of charges, which means there's some potential difference between the ends of that wire. How does that end up looking? Well, we have maybe some collection of charges near a high potential. So we have positive charges over here, and then negative charges over here. And we can see that EA points away from E and EB points away from B. But of course, this field will be stronger than that field, which will tend to have a field pushing that way. And then the non-uniform charge distribution creates a net field to the right at all points inside the wire. So the fact that we have just the distribution of charges on this conducting wire are non-uniform creates a field through it. All right, surface charge is distributed on a wire as shown. The electrons in the wire do which of the following? Well, we know they drift. They certainly don't move upward or downward. And there is a net field on them, so they don't remain at rest. And of course, negative charges move against fields. So we know there's more field pointing this way, so the negative charges move that way, which is leftward. All right, here we have a prototypical graph showing the speed of an electron during multiple collisions, and the idea is that the electron is being accelerated by the field and gets faster and faster and faster, hits the proton and bounces backward. So abruptly is going the other way, but is still moved in the direction against the field and is accelerated by the field and picks up some speed and then hits some other nucleus and is bounced backwards and just kind of does this jagged sawtooth kind of thing. Sometimes it doesn't get turned around, sometimes it does, but there would be some average velocity, all right? But because the acceleration is always in the same direction, the average velocity will not be zero. There will be some drift velocity. And then the average drift speed would be given by these things, where E is the electron charge and M is the electron mass, and E is the typical field, and this tau is the drift time, the average time between collisions of an electron and a proton. That's a thing set by the lattice structure of the metal, and therefore is sort of a physical constant. By the way, notice that this is just a fuzzy Newtonian analysis saying that the drift velocity is something like the acceleration times the time between collisions. All right, that we just say, well, we have this slope, and this average time gives us some average acceleration. And so the force, of course, is the electric field times the charge, and then we divide by the mass to get the acceleration. So there's nothing deep going on here. It is just a kind of strange Newtonian analysis, quasi-Newtonian analysis. Okay, the current is a bulk measure. How many coulombs pass a given point all across the wire? Sometimes it's more useful to have an intrinsic property to talk about, something very granular. So we define the current density and symbolize it by capital J. And yes, we also know that capital J, for instance, is impulse because physics has access to only roughly 52 symbols, and they just get overused, and we have to be careful. We define J as the current divided by the cross-sectional area of the wire. That is, J is the current divided by A. These units, of course, clearly are amps per meter square. By the way, this is a little weird because J is actually directed. It's in the direction that the current actually flows. So J is a vector, even though I is not directed and does not have a vector notation to it. And the general way to get around this is with some calculus, as always. And we would say if we had a surface through which current was flowing that has some normal vector n, and we have J flowing out through it like this, then we would say that the little bit of current that passes through that surface is J dot dA times n hat. and then we'd have to integrate it to get the total current coming out of the surface. That's more complicated than the AP committee is going to ask you to do, so we're not going to dwell on it. Your textbook has some decent analysis of it if you're interested, but it's just some three-dimensional stuff that is the analog to what we're talking about here. All right, so the current density in this wire is what? Well, of course, we do something like J is I over A, which is 8 amps over 2 millimeter squared. So 8 amps over 4 times 10 to the minus 6 meters square, which is 2 times 10 to the 6 amps per meter square. We can find an interesting expression for the current and the current density. Imagine we have in a wire of cross-section A an electron number density, that is number of electrons per unit volume, of n sub e, each electron moving at the drift speed v sub d. In a time tau, they sweep out of volume A vd times tau. In other words, we're talking about this circle sweeps out an area, encloses an area, which is the length, that's vd times tau, times its own area. Number of electrons, then, is the number density times that volume. And they carry total charge, which is 1 electron charge times the number of electrons, right, which is the number density times the area times the drift velocity times tau. And then the charge per unit time, of course, is just Q over tau, which is NE times E times A times VD. And so the density, we just divide out the A, and we get that the density, the charge density in a thing that has an electron density that we know and a drift velocity we know is just the number density times the electron charge times the drift velocity. And that seems like it's useless and out of nowhere, and for the moment maybe it is, but it will come in useful later when we start defining resistivity and resistances.